Hey guys, Shane here. Today in this little video I'm recording here, I'm gonna go over some of the FEA and general FEA tips when doing questions 3 and 4 and what the professor generally wants for the mesh convergence in questions 6 and 7. And the reason why this is honestly pretty straightforward and nice and easy is that in the language here he uses for 3 and 4, he gives a lot of leeway to kind of create whatever geometry we essentially want. The main thing, as long as it's using FEA for a um, fracture problem. So we can do whatever geometry we want and keep it nice and simple for us. In each of these FEA things, we're going to be doing mode one loading. So just load in uniaxial direction, LEFM conditions, linear, elastic, conditions, basically just keeping the maximum uh, stress experience below the yield strength. Past that, we run into plasticity, and there's some weird stuff that I tried doing in the last problem to showcase the plasticity. We had to input some different material properties that I couldn't quite get to work. And as far as data he wants to report is displacements along one of the crack faces. So again, like the top or bottom part is the crack as they separate. He just wants displacements along one of those and along the crack front. So basically from the crack tip going all the way to the edge, he wants the placement for. Find details such as material used, properties, mesh node details, mechanical loading history, basically how we're like what's the actual stress we're doing and the boundary conditions and such. Geometric dimensions, software version number, bounding conditions, so on. So the rest of this is details that we should be providing reports anyway. So nothing here is specifically like new or anything like that. And the main difference between 3 and 4 is the kind of elements we're using. I'll showcase a little later in finer details, but conventional elements is literally just what we've been doing so far. Don't stress about anything new or anything, just use regular elements. And the crack tip singularity elements is essentially in the region around the crack tip itself. Um, you're going to change it to triangles that all kind of converge to the crack tip itself. At the end, it should be a region that kind of looks like this, where you got a triangular element, and all the points of them are going towards the crack tip itself. I'll show you the general idea of how to get to that. All right. So, like any good FEA, first thing we're gonna do is, create our part. And a beautiful part about all this is that, again, it has no specific, um, like parameters, geometry he wants. So all we have to do is just keep it nice and simple and say, I don't know, 40 is a 60 by 60 square. And then from here, we can choose to either do a notch into the part itself, or we can get a bit more fancy, and what Professor probably appreciate is using the crack tool to create an actual crack from like a seam. Later on, I'll show you the crack tool, how to do that. But for now, since he never specified or anything, all it said is do something regarding fracture mechanics and mode one loading. So we're just going to create a little notch. There. Use the trim tool, clean it up a little. This is there we are. There's the sketch. There we are. Boom. Notch thing. We're done. Um, and from here, loads and boundary conditions. There's a couple different ways. The one that, again, because he doesn't specify, all he wants is a load in the uniaxial tension direction. So what I found that's pretty good if you're doing, we'll get to that actually. I gotta do the other steps first. So next, obviously, just going down the tree, curing material to say 30 Pascal, gigapascals, something like that. Cool. Next, creating section we will end up using. Sure, using a material one. Cool. Then we go to the actual assembly, kind of put it all together using part one. Actually go back to this section. Siding section. So we're actually using our material and thickness. And there you are. Now we can actually go ahead and start doing boundaries, conditions, and such. All right. So the boundary conditions I normally like using is um if I'm using a whole part like this, is instead of doing weird things where you got boundary condition in the center sort of deal along the crack tip, then tension in both directions. I like to just keep it simple and just lock the bottom. And then just create a load. Oop, forgot to do step. All right, step. Cool. Yeah. Do a pressure load just in at the top. There we are. Now it's all set up for analysis. Um, when it comes to meshing. So what in his 1017 lecture, he goes over a lot about meshing and some things we can do to improve it. And one of the things he mentioned, because for the student edition, we're only limited to 1,000 nodes. Um, one thing you mentioned is that you can instead cut this in half, sort of deal. So what that kind of entails is really easy when doing editing the sketch. Just simply draw a line side to side right here. Trim all the edges here. Then we have to regenerate the features so we can actually see its effect. So we want to do at the top of this branch, generate, boom, cut in half. And in order to actually like simulate what it's like being cut in half, the professor in the lecture was kind of essentially mentioning to put them on rollers. So in this case, if we took a crack that's in the center and we cut it right down to half because we wanted to get a small area to make the most out of our nodes. Um, in the areas that are not the crack, we essentially put them on rollers. So in this bottom half right here, we essentially put rollers so it can not move in the Y direction, but can be used in the X direction. And if we cut down the middle here, we're cutting down, the middle and the Y direction of the part. So we want rollers here where it's locked in the X direction, but still move in the Y. And one thing that I did mess up on the last one, rewatching the lecture, is that so this whole part doesn't end up like sliding around. What you want to do is one point right here. You want to put a boundary condition at a single point where it's locked in the X, Y, and unable to rotate in Z direction. So everything doesn't slide around. So I kind of mainly set that up in some of these example ones I showcased already. Right there. There we are. We have this. Yeah, you see the boundary conditions here. Boundary condition one on the rollers, where it's locked in the Y direction. And then the pin itself, right here at the dot, where it's locked every which way. So like the previous one, I still got the load in the Y direction, which is a pressure load, make things nice and simple. We don't need to reinvent the wheel or anything. And that's about that. So when it comes to the meshing itself, uh, talk a little about that and trying to get it as best as possible. So the idea is, again, he kind of talks about it in the same lecture about the 30-minute mark and onward is the whole part of the lecture we're talking about meshing, is that he wants it really dense around where you're actually trying to see important things. In this case, would be the cracked tip. So we're going to do some things with the mesh to help along with that to get the element density around here as high as possible. So with that, I'm going to actually just create a partition to help like define the mesh and shape it. Um, Here to here, a partition geometry, which will come handy in a second here. Now it's different, two different spaces, and I've got a line going down and able to create any of these partitions using here, using this button here. And it'll show up in the tree as like a separate feature. So if you need to go back and edit the sketch itself, you can do that. All right. So yeah, going over to the mesh. Um, Let me just double check. Do I have a mesh already? Yeah. Okay. So I got to delete some things. Delete. Oh, okay. Go. So no edges. Cool. So when seeding, I like to do it edge, so you can do it case by case rather than the whole thing. So these areas that are nice and far away do larger sizes in general. All right. And here's where things get a little bit different. So we want the density to be thinner here, sorry, thicker here, and a little bit thinner as we move away. So we're going to go here is introduce a bias right here when doing local seed. And so you can see right here, we could do the minimum size of the element and the maximum size, and it just automatically does a range. So let's say we do minimum size about 0.5, maximum size all the way to the edge, it's like 4. Right here, click apply, you can see right here, you got a nice little gradient. If you face in the wrong direction, you can click the little flip button, and now you can see right here, it's flipped the other way. So double check it's making the right direction. So you can just kind of play around with that number, all the different directions. Here. And this is the reason why I added in that diagonal partition line sort of deal, is so I can help like shape the mesh a bit more in this empty area right here. All right. With all that, go ahead and mesh the part. And look at that. It's nice and dense in this area, and further along, it's thinner where we now have to pay attention to anything. And now we're making the most out of the number of nodes we can use. Obviously, you can change the number to get a lot thinner, thicker, add another reference line, I suppose, going in the complete 90-degree direction, whatever you guys want. But that's essentially how we do that. And to kind of double check that we're doing a-okay with our mesh. It's all underneath that 1,000 nodes, or just for reporting purposes when it comes to the actual um, question in the report. You can go to the query information, ask about the mesh itself. Make sure that up here, the part is actually selected, entire part. You can see right here, we have 230 nodes, number of elements, 217. Um, mentions the type of elements going on, how fit sort of deal, and that's everything. I know sometimes I was having some weird thing going on where um, these two were giving different numbers for some reason. Like, I can't remember from the last problem if it was assembly or part that was giving me only, there's 200 elements, but the other one was saying, yeah, no, there's like 897 nodes going on. So if the number of nodes doesn't make sense for what you're seeing on the screen, just like flip over to the other one and see which one's going on. So yeah, that's the meshing. That's how to get a bit better looking one. And with that, all we have to do is submit the job. That and like the question submits, we got mode one loading. Uh, mode one loading. Let me pull up the actual instructions. Yeah, load one loading LEFM conditions because it'll be below the yield strength because you'll play around with loading, make sure it's all good. And now what we have to do is provide displacements along actual specific lines, along specific edges. So that's what I'll showcase here now. Take a look at the results. And you see right here, everything's proper with the boundary conditions. The crack itself is moving upwards. Everything's looking like what it seems. Um, something I might as well mention right now as well is we're gonna have to be like checking for the maximum strength. And there's some ways in like the history output where you can have it automatically pointed out to you. Or we could do the nice and simple way where we go back to the core information, click on element. Look at that. You just click around for, and obviously it's going to be around the crack tip and you can see the green in front of you. And you can just easily find the maximum stress doing this method rather than going based on this scale or doing some real fancy thing with the output in the job section. There we are. That's how you show the max. So might as well on the screen show you guys how to do that nice and easy. All right. However, what we're trying to do right now is trying to find displacement along here and along the crack tip this direction. So what we're going to do is create some paths in order to read the information in those directions. So the two ones that you're mainly going to be using is node list and edge list. I'll do edge list first. We'll do this one along the crack tip. What you're going to do is add after. And what you're going to do is it's basically selecting based off of the edges of elements. So you want to click on where your start is right here. So you start element number two, and then you click all the way to the last one you want. There we are. Start, end. So it's in the correct direction. You can flip it if you need be. This will be important for like plotting a little bit later. So that's why you want to make sure the start and end is correct. And you're done. Okay. And then if we go to manager, you can see it on here. This is something I was doing a little bit earlier. So yeah, that's that. So the other thing we want is in the crack face direction. So what we're going to do in the same area, create path. And I'll show you the node list, how to do it this way. Add after in the viewport selection. And basically you just clicking along in the nodes. Same thing as with the edges, but this gets a more finer area. And I'll like show you later when I'm instead of to create the crack, instead of just creating a notch using the actual crack tool, the node clicking using the node list is a lot easier. All right, here, okay. And then you can see it. Well, Patu, let's rename that. Here we are. Cool. You see our two different lists. And now to get an actual reading from it, we'll go to, delete this. Uh, some old ones I was doing when setting everything up. So yeah, we're going to go to X and Y data. Now you can either go from the XY data create, or you can use this button right here. Either way, it's the exact same way. And the actual source of our data is going to be coming from these paths that we just made. So we're going to go down here. All right. Now we're going to select which path we want. So if we're going to do the crack tip, go to the crack tip. That's now our X. You do the actual X distance. Um, any anything, I find it easier just leave untrue distance. Choose our Y right here. We want displacement. So displacement, magnitude, and we'll do in the vertical direction. Y. Cool. And we can save the data so we can take a look at it later. Crack tip. And we hit plot. We see this. So because of our boundary conditions and the way the crack is going to do, this is 0. However, if we go back to XY data, path, crack face, the crack face itself, same outputs, all the same. Crack face, face, save, plot. You see, nice little line. And this is how we get these actual charts for everything here. And then if you ever need to go back, if you forgot to do anything to upload to report, you just double click on this XY data and it'll bring it up. And with these, nice easy way, like technically, like somewhere around here, you can like save it to like a clipboard or something. I just use the snipping tool and then copy and paste that into report. And I find that significantly easier than whatever actual set systems they use. So that's that. And how to get the actual reporting. Now, according to the report itself, that was the us doing this through using conventional elements, and I'll show you some things to do in order to use the crack tip singularity elements. All right. Let me open up my other file I got. All right. So with the crack tip singularities, the loading, boundary conditions, all this sort of stuff is going to be the exact same. What it did a little different is the partitions we're going to be using. Essentially, instead of the one line going in to the top right corner here, I created some arcs right here, basically creating regions around the correct tip so we can change the type of elements and do some stuff with the meshing. All right. So like in the little picture I showed you, our goal is to get it to look like this and using these triangular elements. So in these smaller regions, we're going to be changing the element typing. And the way we do that is right up here is assigning mesh controls. Clicking on the region you want. And the element shape is going to be try. All right. We're going to do that for each of these regions. Try. Make sure this one's correct. And important thing to note um, is that when choosing the element shape, you want to make sure this medial axis is turned on. I haven't been able to figure out which one's better if it's quad automated or just regular quad, but either or, you want to make sure the medial axis is turned on because the facing front is on it by default. It just kind of helps again, like it says here, the mesh transitioning between the different element types. So you want to make sure that's on, and boom. Now these two regions are in the using triangles. This is using the squares. You can even take it a bit further, assigning element types. If you wanted reduce integration on or off. And obviously, like in previous homeworks, I think one or two, something like that. This is how you switch between plane strain and plane stress. Ignore that warning. You see right here, three node linear plane stress triangle. All right. And the seating, again, is a lot of like the same thing where you go through, make sure edge by edge, like that further out here is going to be larger element sizes, 35. And then obviously as you get closer here, you want better meshings going on. So right here, this doesn't really need a bias because it's so short and close in. So we'll save that. Too much. Uh, yeah, go with that. All right. And we'll take a look what the mesh looks like. So this is an issue that I've been having a quite 100% been able to figure out. You can see how it's in all these banner directions rather than all facing towards the crack tip itself. This is obviously not what we're looking for. I haven't been able to figure out the magic solution because on my other one that I'm using for question 10, I was able to get it correct where it has a singularity going towards it. So that's something you're going to, whoever's doing this has to quite figure out itself themselves. But the way the method I showed you is in general the way you want to do this. So pulling back up the instructions, that's number four done. And obviously the way you do displacements and everything is the exact same. So one final thing I want to gotta show you is like FEA wise is how to actually use the correct tool. It's not important in this homework, but in future stuff, you're gonna have to actually use the correct tool for certain things. I haven't fully done this, but essentially I have to use the crack tool in order to simulate crack growth. In future homeworks, we have to show like the separation between two different nodes or something, for example. It's going to become important. So going back to abacus here, uh, pull up my other file I've got in standby. Okay, cancel. There we are. So as you can see here, instead of you can see my partition here. Instead of actually creating a notch in the part itself, what I did is just create a straight line with these two different regions. And for all of this part in the large example, my boundary conditions, all the same sort of stuff. You see here, loading up here, locked at the bottom. Spoilers. There we are. All right. And so what we're going to do is essentially take this seam and make this our crack. So the way we do this is by going to the interaction screen here. I save this off. Start from the beginning. All right, there we are. So the way we actually turn this into a crack was go in the interaction screen, make sure it's on the right model, all the way at the top, special, crack. And we start off kind of like with the XY plot where we're plotting our contour line. We're going to assign the seam. I'm holding a shift click as I'm going through so it doesn't deselect everything. Done. Now we see that in the if we go delete seam, it's nice and bolded, so I know I selected it correct. All right. Now turn into an actual crack. Go to create, crack one, type. This other stuff is some other things. I have to watch the video again. I'm pretty sure I have to click on this myself for crack propagation. But in general, if you want to get fancy for this homework, you have to contour integral. Um, First thing you want to do is select the crack front on the contour region. So it's going to be this area. Crack tip itself. Going to be that dot there. The Q vectors, I know in the last homework is specified. It's basically, to my understanding anyways, is the actual direction the crack is opening. So in this case, what I'm going to do is the starting point of the Q vector here and this direction. The most important part is it's a vector, the actual direction. So anywhere along this line for the start and end would have been okay as long as in the -1 direction. So here, the Q vector, that is correct, so I'm good. I can hit OK. And now this seam here is turned into crack. In order to actually purposes later, to actually read it, what we're going to do is create a history output request. Here, load during my actual load step. That's why I named this one. Right there. Instead of the whole model, we're going to click on crack. All right. And that's where this J integral comes in, the way it calculate crack. And I don't know. I don't know the actual number of contours is, but in the video that I originally watched, they threw in 4. So I'm put in 4 for this. Now we got history output for the crack itself. All right. So with all that, oop, forgot the mesh. Um, the mesh is like the same as the singularity, where these two regions I would put into try. Well, in the video itself, they only did the smaller region where it's the triangular element and the outside is the quad. Um, for the most part, again, the main thing is that around the crack tip, you want quad. Here, new, where's my mesh? Yeah, you see, this is how I was able to get it using the exact steps in Singularity. There's some cleanup stuff I have to do. Not 100% sure why it turns out this way, but this right here is the end up goal for that question for you want to get it look like. So with this here, submit. Ignore that notification needed. Go with the results. There we are. You see right here, I got my deformed element using the crack tool. And when doing the X and Y, like I mentioned earlier, because it's kind of hard in the previous one because, it's not separated. What I did that kind of works is while it's in this deformed shape, you go through oop, path there. Path using the node list rather than edge because it freaks out a little bit when doing the edge case. After crack tip, do the edge. Uh, what's that? Come on. Fine. That manager, delete these other ones. Oh, here. After. And then again, so it doesn't freak out like I showed there was a complete straight line. What I've done is I actually click through the different nodes individually. Now you got proper pathing along the upper tip. Okay. Path one. It's looking good. Yield output. Displacement, U2 direction. Boom. We got our displacement plot. So that's how you actually use the crack tool if you want to get more fancy on this one. Professor probably appreciate it more. But again, in the instructions, she doesn't specify anything about geometry or something. So if you want to do the notch case, that's probably okay. And that's how you show the XY data as well to get a nice little chart. One thing kind of wanted to mention as well is 6 and 7 mesh convergence study. Super, super, super simple. Um, Basically, the idea is that we want to see as we have more elements, like we get closer and closer to what the correct stress answer is. So all we really have to do is play around the mesh, change like the number of nodes or elements, however, use the inquiry thing I showed you earlier. Um, this is in the way. There we are. Mentioned earlier. I gotta go back to this. But yeah, if you remember earlier, go back in the video. Mesh, find the number of elements, play around like with different numbers, and just apply in an X and Y graph. Boop boop, until you get towards like an even like a convergent number. And then that's all he really wants from the convergence study anyways. And that about covers everything off the top of my head here. If I missed anything, you have any other questions, feel free to message me. I'll be able to like at least point you in the right direction, hopefully. And that's about everything. Yeah. Hope you guys like hopefully this is helpful and this kind of gives you all the information you guys need. Right? Bye.